Hey guys, in this video I'm going to work through some practice problems related to exam 3 in the fall 2021 semester. I'm going to start with number 1 and see how far I get. And I'll say I haven't seen these problems before, so we may dig into the problem solving process a little bit. We may go down a road that turns out not to be fruitful and have to backtrack. Mistakes may be made, but I really want to show you what problem solving looks like kind of improvised and on the fly, since that's what you'll be doing in an exam type situation. So let's get right into it. Actually, one more thing before we get going. Note that I will be using Wolfram Alpha to do a lot of these calculations. You'll of course be using your calculator. I encourage you, when we get to a point, or when you get to a point where you've got enough numbers to calculate your way through to a final number in a problem that involves a calculation, pause the video and go ahead and do it, because I'm going to be using Wolfram Alpha, for example, for things like physical constants and other things that might appear on your crib sheet or require punching into a calculator, just to save a little bit of time on my end. So let's get right into it with problem number 1. In this problem, we have an energy that we're looking for of a collection of photons, specifically 10.40 moles of photons with a given frequency. And I know this is a frequency because I'm dealing with light and the units are inverse seconds. I want that energy in kilojoules. I'm going to go ahead and note that down. I want the energy in kilojoules. And I know the frequency, and this suggests that I need an equation that's going to relate energy and frequency of light, and there is an equation that does so, E equals h nu. Now that equation is for a single photon. If I've got a collection of photons, it's going to be the number of photons I've got in absolute or raw terms, we'll come back to that in a second, times h, which is Planck's constant, times nu, which is the frequency. Now the frequency is given in the problem. Let's go ahead and get that down. It's 2.84 times 10 to the 12th per second, or hertz equivalent units. And Planck's constant is a physical constant that you should have on your crib sheet, ideally in units of joule seconds. This is going to make life easiest. In all honesty, though, I'll probably provide the values of physical constants where they're needed on the exam. In any event, the value of h is 6.626 times 10 to the negative 34 joule seconds. That is the value in joule seconds, and we can see that joules will pop out when we multiply the frequency in inverse seconds times Planck's constant in joule seconds. What about this in value, the number of photons? Well, we're given a number of photons in moles, 10.40, and this is a perfectly valid number of moles in the same way that 12 dozen donuts is a perfectly valid number of dozens of donuts, but it doesn't tell us the absolute number of photons we're dealing with. In order to find that, we need to multiply this 10.40 moles times Avogadro's number, 6.02, 6.022, let's add an extra digit, why not, times 10 to the 23rd, and the units of Avogadro's number actually are inverse moles, so this is going to give us just a raw number of photons that we're dealing with. So we can then plug these numbers in, and let's go ahead and do that. 6.022 times 10 to the 23rd. We've got 10.40 moles. We've got Planck's constant, 6.626 times 10 to the negative 34. And we've got the frequency, 2.84 times 10 to the 12th per second. Now the number that pops out of here is going to be a value in joules. Good. And the number of joules that pops out of here is 11,785 joules. And of course, to convert to kilojoules, we're just going to divide by 1,000 or multiply by 1 kilojoule for every 1,000 joules. Nothing too fancy there at all. And we're going to arrive at 11.79, let's say, kilojoules. And we can go ahead and pop that in for question 1. Done and done. And just as a quick sign check, that number should be positive since photon energy is positive.